Welcome back. In this final installment of our series, we will wrap up our guitar application with more complex interaction. By utilizing JavaScript functions, we can respond to user input in a more dynamic and interactive way. We will create dial components that visually indicate the adjustment of various aspects of a guitar's sound. This will build upon our previous knowledge of interactive elements and make the UI of our application behave more closely to a physical guitar pedal as a user might expect. Our final journey starts with creating an inline component once again. We'll define DeviceDial as an image component representing the dial's base, the markings around the edge of the dial that let the user know what value they have selected. Next, we can add the dial's knob itself and center it within the component. To see how our component is progressing, we can place an instance within our application to see what it looks like somewhere in the center of the app, just below the LED and mode switch. Let's build and run to see the result. The placement is good, and we can now visualize what is happening as we add functionality and other elements. The user should know what each instance of a dial does and what the range of the dial means when it is moved. How can we do this easily? In the last section, we created a component to do just this. We can use some instances of the previously created device text component to add a min and max label and one for specifying the dial's name. Starting with the min and max labels, we can add two instances to the DeviceDial component, position them to the bottom left and right, respectively, and make the font size smaller to leave space for the larger name label in the middle. We want the name label to be modifiable per instance, so we can use a property alias to attach this to the final device text. Remember to add an ID to the component to specify which device text component we want to update with the property alias. Now we can update our instance to specify the dial's name and run the app to view our changes. Great! Now we have the visuals of our dial. We need to think about how we want this component to react to user input and explore how this is possible with Qt Quick. So, the dial needs to rotate between the minimum and maximum markings of the dial. The rotation will correspond to a particular value between a minimum and maximum that could be used to control the sound of our guitar pedal. Let's define some properties we can use to build this functionality. We will create 5 properties: value, angle, minimum value, maximum value, and range. This will enable us to set the current value of the dial based on the angle and specify the values and range in which it operates. Notice that we are setting minimum value, maximum value, and range as read-only. What does this mean? This means that the values cannot be edited during the application's lifetime and will remain constant, reinforcing data integrity and predictable behavior. To enable interaction with our dial, we will add a DragHandler component. What is a DragHandler? The DragHandler in Qt Quick is a component that detects and manages drag actions within a QML application, allowing elements to react to user drag inputs. It's particularly useful for interactive UI elements that require user manipulation, such as moving an element across a user interface. Think about how you manipulate and reorganize the icons on your phone's home screen. For us, DragHandler has a useful property called centroid. The centroid property of the DragHandler is central to calculating the dial's rotation. It represents the average position of active touch points, or the mouse's position as you click and drag. This position, relative to the dial's center, determines which way our dial should point, and therefore the angle and value of the dial. Here is where JavaScript comes into play. Various parts of QML documents can contain JavaScript code. JavaScript code can be used in the body of property bindings and signal handlers. You can also define custom methods inline or in a separate JS file. For our app, we will create an inline custom method that's called every time the centroid, mouse position, changes when we press the left mouse button. When adding the DragHandler, we don't want to move the dial itself around our application, only update its rotation. So, we need to set the target to null. Now we can set up our inline function. We'll create a new function called update value and rotation, and start by checking if the pressed button is not equal to the left button. If so, we want to exit from our function. Then we can calculate the relative position of the mouse, centroid position, to the center of the dial. YY is the vertical difference, and XX is the horizontal difference. We now need to get the angle in degrees of rotation. We can start by getting the angle in radians using the math atan2 method and convert it into degrees. For this, we need to negate radian angle, so we rotate clockwise. We also need to adjust the algorithm by adding 90 degrees. This adjustment aligns the angle calculation with how the dial image is visually represented in its default state. Let's now connect our function to the signal handler that responds when the mouse position is updated. We can then set the rotation of our dial to the angle property and see what happens. Great! Our dial moves, but there are still a few things left to fix. We need to make sure the dial stops when it reaches the minimum and maximum points of our dial range. So let's create two properties for this within our function for the start and end angle. We can now clamp the values between the start and end. Let's also add a console log to see what values we get from our dial. Rotating our dial clockwise, we can see that it reaches the maximum of 140. But what if we rotate counterclockwise? The dial reaches -90 and then jumps back to 140. Why is this? When converting radians to degrees, we usually get values between -180 and 180, allowing us to rotate toward the shortest path's direction between the circle's midpoint. However, we are adding a 90-degree offset to accommodate the default state of our dial image facing upwards at the start, effectively changing our range to between -90 and 270. This means we have an issue here. The value range we want for our dial is between -140 and 140. So we need to shift new angle back to this useful range of -180 to 180, and then we have the range clamped as before. We can start by calculating the difference between the new angle we want the dial to point to and the current rotation of the dial, effectively saying, I want the dial to move this much from where it is now. Adding 180 degrees moves the entire scale up, so we avoid negative numbers in the next step, which involves the modulo operation. The modulo operator % returns the remainder of division by the specified amount, 360. This step ensures that our numbers fit within a full circle, 0 to 359 degrees, by wrapping around if the number exceeds 360 or falls below 0. It's a way to keep our angle within the bounds of a circle. Finally, we adjust the result back to the original rotation of the dial and then shift it by subtracting 180 degrees. This adjustment aligns the new angle with our original reference point, dial starting pointing upwards, and fits it within the new range of -180 to 180 degrees. Finally, we want to set the value that our dial will output based on its angle. Let's start by finding the difference between the dial's current angle and the start angle. This difference shows how far the dial has been turned from the starting position. Next, we'll take the difference and divide it by the total angular distance between start angle and end angle. This division essentially calculates what fraction of the total angle the current position represents. For instance, if the dial is exactly halfway between start angle and end angle, this operation results in 0.5, indicating the dial is 50% through its total possible rotation. Finally, this fractional value is multiplied by the dial's range. This multiplication scales the fraction to the range of values the dial can represent, translating the dial's angular position into a specific value within this range. Our dial's range is 0 to 100, and if the dial is halfway through its rotation, the resulting value would be 50, accurately reflecting the dial's position in terms of its range of possible values. We will also output this value to the console to see if it works as intended. Let's test it out. Our dial is working as intended and the values are correct. Let's wrap up by adding 2 more dials. In this final section, we have explored more complex interactions within our guitar pedal app, integrating JavaScript functions to build responsive user input and feedback. We introduced dials that mimic more tactile physical controls, enriching the user interface with dynamic interactivity and visual feedback, rounding off our journey from basic setup to a fully fledged cute, quick application. Across the 5 sections, we've embarked on a comprehensive journey covering Qt, Quick, and QML to create a guitar effects pedal app. We started with setting up our project and progressively built a visually engaging and interactive app. We've explored adding background images, creating custom components, handling user input, and incorporating complex interactions, each step making our app more intuitive and closer to a real guitar pedal. This journey not only introduced fundamental concepts of QML and Qt Quick, but also demonstrated the power of modular design, property management, and user engagement in application development.